Hi students, in the previous chapters we've learned so much about carbon and its compounds. We've learned about the covalent bonds that carbon shares with hydrogen, bromine, chlorine and other compounds. We've learned about, the different structures of alkanes, alkenes and alkynes. We've learned about ethyl alcohol or ethanol as they call it, and we've learned about ethanoic acid. We have even learnt about, soaps and detergents and how they clean clothes. In this particular section, let's summarize all that we've learnt in this chapter. That will instill the concepts clearly in your mind, isn't it? Here we go. First of all, in this chapter, we learned that carbon compounds are everywhere. Be it a glass bottle, a piece of wood, a paper, or even the computer in which you're viewing this video. Everything, almost everything around us is made up of carbon. Why is it that carbon has so many compounds? Well, we learnt in the previous chapters that this is because of two reasons: the tetravalency of carbon and the property of catenation. Catenation is the property of carbon to form carbon-carbon chains. Carbon forms carbon-carbon chains which are stable because of its small size. Carbon is tetravalent, so it can form 4 bonds. 4 bonds is a large number of bonds, which is why carbon forms a large number of compounds. These are the two reasons for that. Then we also learnt in the previous chapters, exactly what a covalent bond was. We learned that in a covalent bond, 2 atoms share electrons. When one pair of electrons is shared, we call that bond a single bond. So here you can see a molecule of methane. In this molecule, carbon needs 4 electrons, while each hydrogen atom needs 1 electron each. Therefore, carbon shares 4 of its electrons with 4 individual hydrogen atoms to form 4 covalent bonds. Understood? Here you go. This is the structure of methane. We learnt about all this, in the previous chapters. Then, of course, we learned that carbon forms covalent bonds with a large number of compounds, with hydrogen, with oxygen, with nitrogen, with sulfur, and many other compounds. The crux is that carbon always, shares all 4 of its electrons when it forms covalent bonds. Understood? So we learnt about all this. Then, of course, we learnt about some special categories of carbon compounds called alkanes, alkenes, and alkynes. Alkanes are hydrocarbons or carbon-hydrogen compounds which have only single bonds between them. Standard formula of alkanes is CnH2n plus 2. We learnt about alkenes. Alkenes have one double bond between 2 carbon atoms in a hydrocarbon. The formula of alkenes is CnH2n. We learnt about alkynes. Alkynes share a triple bond between 2 carbon atoms. The general formula of alkynes is CnH2n minus 2. We also learned that the simplest alkane is methane, CH4, then C2H6, C3H8 and C4H10. We have methane, ethane, propane, butane, pentane and different such alkanes. We learnt about all these alkanes. This, for example, is the structure of propane. As you can see, 3 carbon atoms are arranged one after the other, and you can see that hydrogen atoms are attached to the carbon atoms in such a way as to maintain the valency of carbon as 4. We learnt about alkenes. We learned that the simplest alkene is ethene. Then we have propene, butene and pentene, isn't it? Of course, since the general formula of alkenes is CnH2n, we have C2H4, C3H6, etc. This is the structure of propene. As you can see, there is one double bond between the 2 carbon atoms of propene, isn't it? We learnt about alkynes. The simplest alkyne is ethyne. Then we have propyne, butane and pentyne. Here's the structure of propyne, which has a triple bond between 2 carbon atoms. After learning about all these, alkanes, alkenes and alkynes, we learnt what a homologous series was. A homologous series is a series of hydrocarbons or carbon compounds which differ by the group CH2. Members of a homologous series have similar chemical properties. The series of alkanes is a homologous series. As you can see, CH4, C2H6, C3H8, all of these differ by CH2. Similarly, the series of alkenes is also a homologous series. C2H4, C3H6, C4H8, all these differ by the group CH2. So these are two examples of homologous series. We also learnt about different functional groups. Functional groups are special groups of atoms that impart special properties to alkanes. Basically, we replace a hydrogen of the alkane with a functional group. This is the halo group, the alcohol group, the aldehyde group, the ketone group, and the carboxylic acid group. We even learnt about the naming of the compounds that contain functional groups. Compounds which contain the halo group are named haloalkanes. Compounds with the alcohol group are called alkanols. Compounds with the aldehyde group are called alkanols. Compounds with the ketone group are called alkanones. And compounds with carboxylic acid group are called alkanoic acids. We learnt about all these. We also learnt about the formation of coal and petroleum in this section. We learned that coal was formed when plants and animals that existed millions of years ago got decomposed under the land. We learned that petroleum was formed when sea plants and animals that existed millions of years ago got decomposed. Then we learnt about two special carbon compounds, ethanol and ethanoic acid. We learnt about the different reactions of ethanol, the reaction of ethanol with sodium, the reaction of ethanol with ethanoic acid, the reaction of ethanol with oxygen, and so many other chemical reactions of ethanol. This is the structure of ethanol. We learnt about ethanoic acid, the reaction of ethanoic acid with ethanol, which is called esterification. We learnt about the saponification reaction related to the formation of esters using ethanoic acid. We learnt about the reaction of ethanoic acid with carbonates and bicarbonates. Ethanoic acid evolves carbon dioxide gas with carbonates and bicarbonates. Here's the structure of ethanoic acid. After learning about all these things, we learnt about the action of soaps and detergents. We learned that every soap molecule has a hydrophilic end and a hydrophobic end. The hydrophobic ends get attached to dirt particles and they form a spherical ring around the dirt particles. The hydrophilic ends or the water attracting ends are the sodium ends and they point away from the dirt particle and they get attracted to the water. So basically, soap molecules form spherical aggregates called micelles like this, which trap dirt particles and then make them dissolve in water or make them get dispersed in water. Dirt particles which are initially insoluble in water start dissolving in water because of the action of soap. So there you go. We learnt about all these things in this wonderful chapter related to carbon and its compounds. Hope you enjoyed the entire chapter. Let's now proceed to the next section.